Welcome to Crystal Clear Chemistry channel. In order to crack either JEE mains or NEET exam, let's strengthen our basics of chemistry through this channel. In this video, I am going to discuss the part 2 of ionic equilibrium. In this, the first topic is the degree of dissociation, which is represented by the letter alpha. Degree of dissociation in the sense, if we consider any electrolyte, for example NaCl, it readily dissociates into Na plus plus Cl minus. If the electrolyte is very strong, then it completely dissociates. Then if we take 1 mole of NaCl, all that 1 mole of NaCl molecules dissociate, so that you will get 1 mole of Na plus ions and 1 mole of Cl minus ions in the case of strong electrolyte. But it is not true in the case of weak electrolyte. Suppose if we consider the weak electrolyte like CH3COOH, for 1 mole of CH3COOH, only 0.7 or 0.6 moles of CH3COOH undergo dissociation or undergo decomposition. So here, uh, if the electrolyte is very weak, it is far less than 1 mole of electrolyte will undergo dissociation. To measure that dissociation, we have the letter alpha, which is called degree of dissociation. The formula for degree of dissociation is how many moles we have taken, so that how many moles are dissociated. The number of moles are dissociated by number of moles taken is nothing but alpha, and this alpha is 1 for strong electrolyte, alpha is less than 1 for weak electrolyte. Okay, so suppose if we consider the degree of dissociation, the dissociation or ionization definitely depends upon the factors like nature of solvent, dilution, temperature, etc. The solvent with dielectric constant favors the dissociation, hence alpha increases. On dilution, the ionization increases, hence the alpha increases. And whenever the temperature increases, generally the degree of dissociation increases. And if we consider the presence of other solute, if any common ion is there, the electrolyte dissociation is suppressed, hence the degree of dissociation decreases. And we have the dilution law also, where you can see in another chapter, but here as we discussed about the alpha, let's discuss about the relation between alpha and concentration with the help of Ostwald dilution law. So with the decrease in the concentration, the alpha value increases from 0.1 to 1. You can see here clearly. So we go back because we are decreasing the concentration. With the decrease in the concentration, the alpha value is increasing in this manner. Okay. In the ionic equilibrium, alpha we use for weak acid and weak base, and we have to draw some relations also in order to solve some of the problems. Okay, so suppose if we consider the weak acid, like HA is the let us suppose that HA is the weak acid, it readily dissociates into H plus and A minus ion, and that H plus ion reacts with H2O, so that hydronium ions will be formed. Generally, we write the protons concentration in terms of hydronium ion concentration, and at equilibrium, whatever the equilibrium constant is there, we take that as a dissociation constant, and hence here Ka is the dissociation constant of acid, where you are getting H plus into A minus divided by Ha, and here Ka is the ionization constant of acid. You can see the expression here. Now listen carefully. Suppose if we consider that ionization constant of acid, it is around 1.8 into 10 to the power of minus 5 at 298 Kelvin. Okay, at that means at room temperature, you can say 25 degrees centigrade. Then if we consider the HF is a strong electrolyte, you can clearly see the difference. KHF is very high, it is 6.7 into 10 to the power of minus 4. So depending upon the Ka value, dissociation constant of acid value, we can say the strength, higher the Ka, higher is the acidic strength. So conclusion here is Ka is more means it is more acidic in nature, or you can say stronger acid than the less Ka acid. Okay. Now, how the alpha helps here? Let us see. Now, let us suppose that we have taken the C moles of CH3COOH. For 1 mole of CH3COOH, alpha moles are dissociated. Then, in case of the C moles, C alpha moles will be dissociated. If C alpha moles are dissociated, the H3O plus concentration is C alpha, right? Sorry. And CH3CO minus concentration also C alpha. In that case, the dissociation constant of acid Ka is nothing but C alpha square by 1 minus alpha. Now, in the case of weak electrolyte, as 1 minus alpha is almost equal to 1, as alpha is very less than 1, if you substitute, you will get a Ka is equal to C alpha square, and alpha is equal to square root of Ka by C, where H plus ion concentration you will get as C alpha, because we know already in the case of C alpha. See here, H3O plus concentration is C alpha, and hence C into alpha means square root of Ka by C. If we substitute, you will get the other expression square root of Ka into C. As of now, what we need to remember here, we have three formulas so far. Ka is equal to C alpha square by 1 minus alpha, and we have H plus ion concentration nothing but C alpha, and we have another relation that is nothing but uh, alpha is equal to uh, see here, alpha is equal to H plus ion concentration is equal to C alpha, alpha is equal to square root of Ka by C. All these formulae are very useful to solve some of the problems. So we came to know that the Ka is dissociation constant, more the Ka, more is the acidic nature. It is similarly we can draw the relationships for the weak base also, where you will get alpha is equal to square root of Kb by C, and the OH minus concentration is C alpha, right? It is for weak base. Now, let us see what is ionic product of water. Ionic product of water is nothing but uh, the H plus ion concentration into OH minus ion concentration. It is represented by the letter Kw, which is nothing but H plus into OH minus. This is ionic product of water. How we can get the ionic product of water means, suppose if we consider the water dissociation, and here dissociation of water or ionization constant of water, you can write in like this, products by reactants, and here you can see uh, as H2O concentration is constant, and as it is a pure liquid, we can say H2O concentration is constant, and hence you can take it as a unity or constant, and you can get the H plus ion concentration into OH minus ion concentration. This K dissociation constant of water into water concentration, you will get it as H plus into OH minus. So Kw here is the ionic product of water. Just try to remember, either in the aqueous solution or in either the aqueous solution of uh, the neutral electrolytes, or for the water, H plus ion concentration is always equal to OH minus ion concentration, and the value is 10 power minus 7 at 25 degrees centigrade. So conclusion here is ionic product of water is nothing but Kw. It is the hydronium ion concentration into the hydroxide ion concentration, its value is 10 to the power of minus 14 moles square per liter square, because the hydronium ion concentration or OH minus ion concentration at 25 degrees centigrade is 10 power minus 7. Okay. Now, ionic product of water we came to know, and even we know already about the dissociation constant of water, right? What is the dissociation constant of water? Um, See here, why we are getting this 1.8 into 10 to the power of minus 9, what is this 55.55 and all, let us see. Already discussed, we discussed here, see here, concentration of water is very high, that is 55.55 moles per liter. Okay, and we have, and we have that 10 power minus 7, 10 power minus H plus ion concentration and OH minus ion concentration. So 10 power minus 7 into 10 power minus 7 by 55.55. Then you will get 1.8 into 10 to the power of minus 16 as the answer. Okay. This is called degree of dissociation, and this is the dissociation constant. Both are different. You can see the difference here in the value. Okay. And here the Kw is the dissociation constant into 55.55. Regarding water, you can remember these formula. Thank you. That's all about the second part. Thanks for watching the video.